Okay, calculus, 12.2. If we can do the limit, you know what else we can do. Calculus always leads this way. The derivative of a vector value function is almost exactly like the derivative of a regular function, the limit of r of t plus delta t minus r of t over delta t, which should look exactly like f of x plus h minus f of x over h. Now, if the derivative of the vector value function, the derivative exists, then it's differentiable at t. If r prime of t exists for all t, then r is considered differentiable on the interval. Differentiability of vector value functions can be extended to closed intervals by considering one-sided limits. If you have a bunch of functions in your components, the derivative of the vectored value function simply comes about by taking the derivative of the components. Should be easy because most of the functions we'll work with are not that complicated because we're extending them from previous experiences. So let's see how this works. For the vectored value function, r of t equals ti plus t squared plus 2j, find r prime of t and sketch the curve. Okay, so r prime of t. I need to take the derivative of t with respect to t, so that's 1. The derivative of t squared plus 2, with respect to t, it becomes, again, the power rule, 2t, 2 goes away. Okay, so let's find the vectored value function and sketch. Well, how do we sketch this? You ask yourself. Our x component is t, so this is just a normal x component. Our y component would be the equivalent of t squared plus 2. But if x is t, that means this is really y equals x squared plus 2 by just substituting in there, which we should know is a parabola moved up 2. We'll be able to confirm this shortly. Now, what about the derivative? Let's confirm r of 1, since it asks for 1. R of 1, based on this equation, is just 1i plus 3j, which confirms when t is 1, we should be at the point 1, 3, which is here. Now what about r prime of 1? Using this function, it should just be 1i plus 2j, which is the equivalent of saying the slope at that point is change in y over change in x, 2 over 1. So basically, it's the tangent line at that point. Which, thinking about it, if we talk about what derivatives for a parabola in the past was, it represented the instantaneous slope at that point. So this kind of represents the vector representing the instantaneous slope at that point, because in the end, a tangent line is really just kind of an infinitely length vector. Now, one thing to note, higher order derivatives work exactly the same. If you need the second or third derivative, you take the second or third derivatives of all the components. So for cosine ti plus sine tj plus 2tk, find the following. R prime of t. So the derivative of cosine is negative sine t. I'm going to write it in vector form. Derivative of sine is cosine t. The derivative of 2t is 2. Second derivative. Derivative of negative sine is negative cosine t. Derivative of cosine is negative sine t. The derivative of 2 is 0. Now I'm going to bring c and d down. Okay, now it says it wants the dot product of these two things. Okay, dot product. Negative sine times negative cosine becomes positive sine t cosine t. Cosine times negative sine becomes negative sine t cosine t. 2 times 0 is 0. Well, these two will cancel out, so this whole thing is 0. And lastly, part D says the cross product. So we do I, j, k. We've got negative sine of t, cosine of t, 2. Negative cosine t, negative sine t, 0. Do your multiplication. Should be I times 0 minus negative 2 sine t minus j times 0 minus negative 2 cosine t plus k times, looks like, sine squared t minus negative cosine squared t. So sine squared minus negative cosine will become sine squared plus cosine. Minus and negative becomes positive, so it's 2 sine t I minus 2 cosine t j. Sine squared plus cosine squared will become 1, so it just becomes plus k, or 2 sine t negative 2 cosine t 1. So these are some operations we can do with our derivatives of vector value functions. Many more to come. Now, a vector value function is smooth on an open interval I if the derivatives of each parameter of the function are continuous on that interval and the derivative itself overall is not equal to 0 at time t. So if r of t equals f of ti plus g of tj plus h of tk is continuous, the first derivatives for each component, continuous on I and r prime of t is not equal to 0 for any time in the interval, a function can be smooth over certain intervals without being smooth over the whole domain. So find the intervals on which the epicycloid defined by the function below is smooth. So we have r of t equals 5 cosine t minus cosine 5 ti plus 5 sine t minus sine 5 t j between 0 and 2 pi. Let's talk about the derivative. Derivative of 5 cosine t minus cosine 5t should be negative 5 sine t plus 5 sine of 5t by chain rule. Derivative of the second part, 5 cosine t minus 5 cosine 5t j. So ask yourself, when is negative 5 sine t equal to negative 5 sine of 5t? When is this 0? When sine t equals sine of 5t. And this happens at t equals 0. It also happens at, let's see, probably t equals pi over 2. Maybe pi over 2, 5 pi over 2 are the same. Pi, 5 pi, the same. This is 4 pi ahead. It's 2 pi ahead, it's 4 pi ahead. There could be more, but at least at 0 we know it's true. Same thing over here. When is 5 cosine t equal to 5 cosine 5t? When cosine t equals cosine of 5t. This happens when t equals 0, and again for every pi over 2 after that at least. Okay, so what does that mean? It says it's smooth if the derivatives are continuous on the interval and the derivative itself overall is not equal to 0 at time t. Even though these are equal, the derivative is not 0 at time t because cosine, actually it should be 0 at time t. So it's definitely not smooth at 0.